Okay, so our oxidation and reduction or redox reactions um, involve the transfer of electrons. Now, we define the process of oxidation as the loss of electrons and the process of reduction as the gain in electrons, and these processes occur in tandem. Now, one of the hallmark features of oxidation is that when an element loses electrons, becoming oxidized, it increases in charge. And we say that the oxidation number of that element increases due to the loss of electrons. Now, when we're dealing with metals undergoing oxidation, this is simply seen as a change in the charge. That is, the metal becomes more positively charged, whereas in reduction, the oxidation number of the element decreases as that element gains electrons. So we can see this pretty simply in some of our metal examples. And so in determining what is being oxidized and what is being reduced in a chemical reaction, we want to pay attention to the oxidation numbers. And in this video lesson, we are going to talk about the rules for determining the oxidation numbers in our reactants and products. Now, for some of the simple examples that we've seen already, um, when we're dealing with metals, we really just need to pay attention to the charge of those metals. So for example, when we reacted zinc metal with aqueous copper ions, we underwent a spontaneous redox reaction to produce aqueous zinc ions and solid copper metal. And in this process, we noted that it is zinc that is losing electrons, that is, it is being oxidized, while copper is gaining electrons and it is being reduced. So when we look at this process, we look at the oxidation numbers. That is, initially zinc has an oxidation number of 0 because it's a neutral element, and it has an oxidation number equal to its charge, which is +2. So the oxidation number increases, whereas copper does just the opposite. It goes from a +2 to a 0 in the copper metal. And so for metals, the oxidation number is simply equal to their charge. But in other cases, it is not as straightforward. And so we will review now the rules for determining oxidation numbers in most simple cases. So the first thing to recognize is that whenever we are dealing with an elemental substance, by definition, the oxidation number is 0. That is, if the element is not combined with other elements in a compound, we say that the oxidation number is 0. So if it's metallic copper, it's 0. If it is aluminum, and it is a solid, as in a metallic aluminum, the oxidation number is 0. Okay. Similarly, if we have elemental substances such as hydrogen, oxygen, nitrogen, any of our halogens, fluorine, chlorine, bromine, or iodine, these all have an oxidation number of 0 because they are uncombined with other elements. So that's by definition. Now, when we are dealing with monoatomic ions and in ionic compounds, the oxidation number is simply equal to the charge. So, for example, in the compound magnesium chloride, we have a +2 magnesium ion, so its oxidation number is +2. And then we also have 2 chloride ions, which each have a -1 oxidation number. Okay, so it's simply equal to the charge of that monoatomic ion. When we form the compound, we need 2 of those chlorides to balance the +2 charge of our magnesium. And this brings us to our third rule, which basically says that for all compounds, The sum of all of the oxidation numbers must be equal to 0 for those neutral compounds. And when we're dealing with polyatomic ions, the charges will, or the oxidation numbers will sum to equal the charge of that ion. Okay, and we'll see some more examples of this, but let's do one more quick one. Let's say we have a compound such as aluminum oxide. So we have Al2O3 is aluminum oxide. We know that in this compound, aluminum is an ion with a +3 charge, so its oxidation number is +3, whereas the oxygen has a -2 charge, and we will say its oxidation number is -2. Okay, and so we have 3 oxygens at -2 for a -6, and we have 2 aluminums for a +6 charge, and they balance out to a net neutral 0. Okay. Now, so for all compounds, the sum of the oxidation numbers is 0. And so generally, if we know the oxidation number of one element in a binary compound, we can figure out the other. And so it's useful for us to know 3 particular elements that are usually easy to predict. The first of these is fluorine. Anytime we have fluorine in the chemical formula of a compound, the oxidation number on each fluorine atom will be -1. Fluorine is our most electronegative element, and it always has a -1 oxidation state or oxidation number. So for example, if we have carbon tetrafluoride, CCF4, each of these fluorines has a -1 oxidation state, and therefore when we look at that carbon, since there are 4 fluorines, each with a -1 oxidation state, carbon must be +4 to balance the 4 negative ones of the fluorine. Okay, so fluorine is always -1. The only time fluorine is not -1 is when it's an elemental substance, molecular diatomic fluorine. The other 2 elements that are useful to remember are hydrogen and oxygen. Now, in most compounds, hydrogen is going to have a +1 oxidation state. There are a few exceptions to these next two rules, these 2 elements, but we're not going to worry about these exceptions. So when we have hydrogen in an acid, for example, hydrochloric acid, the hydrogen is +1, and the chlorine is going to be a -1 because they balance. Oxygen is usually going to be -2. So if we have the compound water, H2O, hydrogen is going to be +1, and there are 2 of them, and our oxygen will be -2. Now, once again, this allows us to use these elements, hydrogen, oxygen, and of course, as we said, fluorine, to predict the oxidation state of other elements. So, for example, if we had the compound carbon dioxide, CO2, carbon in this compound, we need to know what it's paired with. In this case, each of those 2 oxygens is going to be -2, telling us that our carbon, to balance that oxidation state, must be a +4 because there are 2 of those oxygens. On the other hand, if we had carbon in the compound methane, CH4, we know that each of those hydrogens is +1, and there are 4 of them. So therefore, that carbon now must be a -4 oxidation state. So we're going to use the oxidation states of either carbon or of either oxygen or hydrogen to predict the oxidation state of the other elements in a particular compound. So let's try one more as an example. So here we're going to go HClO4. This would be perchloric acid. So in this compound, we're going to look at the oxidation states of each of the elements. So we're going to, and we want to know the oxidation state of each element. And when we do this, we only want to consider one atom at a time, remembering that the sum of the oxidation states of all of the atoms must add up to 0. So here we have hydrogen, and we remember that hydrogen always has a +1, and there's only one of them. And then oxygen is always going to be a -2, and now we have 4 of them. Okay, so our 4 oxygens are going to be a total of -8. Then we have a +1, and so the difference here between +1 and -8 is going to be the oxidation state of our chlorine. So chlorine must be +7 in this compound perchloric acid. On the other hand, if instead of perchloric acid we had chloric acid, now once again our hydrogen is +1, our oxygens are still -2, but there's only 3 of them. And so now our chlorine, rather than being a +7 oxidation state, is now in a +5 oxidation state. 5 plus 1 is a total of +6, and we have a total of -6 charge from our oxygens. So we can use these simple rules to determine the oxidation state of most elements in compounds. This is going to allow us to predict in chemical reactions what is being oxidized and what is being reduced.